But here comes the fun part. Let's do a bunch of experiments. Okay, again, I have a bunch of experiments listed so that I don't miss anything. So imagine if m equals to n equals to 100. Okay, let's start doing some experiments. M equals to n equals to 100, and we are saying that our significance level is, let's say, 5%. Everything else stays the same. Let's assume k equals to first 1000. Okay, let's write down all these, right? Actually, it's good to write down so that, I mean, it's like tabulating our results. Okay, so let's write down this table. So what is n? Sorry, what is n? What is m? What is k? And what is the p-value that we obtained? These are the four things, right? Oh, there is another thing. What is the, okay, so what is the alpha value for, when I say alpha value, okay, xc is alpha value. Alpha here is not the significance level, it is the parameter of the Pareto distribution. Okay, so xt is alpha value, right? And then we will compute the p-value. Okay, so let's just fill this quickly. It doesn't take much time. Running this code takes like literally 10 seconds. Okay, let's start doing a bunch of let's understand what's happening here. So initially we have, again, this is how you do simulations, right? Your n equals to 100, your m equals to 100, your k equals to 1000. Typically k, we take large values. Okay, your xc, what is our xc and xt here? Again, your xc is a Pareto distribution with alpha equals to 10. Your xt is Pareto distribution with alpha equals to 9. Again, these results will change if the distributions change. Let's not forget that. This is Pareto with alpha equals to 10. This is Pareto with alpha equals to 9. Okay, now let's see what happens to the p-value. Again, what is the ground truth here? Let's also write that, right? So what is the truth here? The truth here is that xc and xt are not the same. Let's explicitly write that, right? Okay, let's also write that. What is the ground truth? The ground truth is that xc is not equals to xt. That's a ground truth. Okay. In this case, let's see what happens first. Okay, if I run this whole experiment, we have the code, right? It takes literally a couple of seconds to run the whole thing. Okay, let's run this. This is simple simulation. Okay, I'll run this whole cell, and I think it'll take a couple of seconds to run it. Let's see what it shows us. Okay, so these are two distributions, right? This purple line is the distribution of control. This green line is the distribution of treatment. Then, okay, our observed value that we got. Look at this. Our observed value that we got is 0.02. This is m observed. Okay, so let's remember this. Your m observed is 0.02. Let's say this whole data is not in minutes but in hours. Okay, your p-value that you got is 0.083, which means it is 8.3%. That's the p-value that you got. Okay, so let's write down the p-value here. The p-value that you got is 8.3%. Okay, now look at, again, we are only doing 1000 we are only repeating this experiment 1000, the resampling times. We are only sampling it 1000 times. Now, what is this? This is the distribution. Look at this. This is the distribution. This is very important. This is the distribution of M. This is the PDF of MIs that are generated under null hypothesis. As I told you, right, this distribution, if you see this distribution, again, there are two bumps here, but roughly speaking, it looks like a Gaussian distribution with the mean at somewhat like 0. This looks like Gaussian. It's not exactly Gaussian. Looks like Gaussian. Okay. Again, just wanted to get that visualization, right? We saw this earlier, right? So we saw this. It is this distribution that I'm talking to you about. Same distribution. Now, one thing that you can observe here is this. What is the value that we observed? M observed is 0.02. Where is 0.02 here? Your M observed is somewhere here. Your M observed is somewhere here. So now, what is the area under this curve? It is not too small. Actually, M observed is not too extreme. It is not too extreme. It's M observed is not here. M observed is still in an area where there is enough density here. So this whole area was 8.3%. I think that's what we saw right now, right? Yeah, we saw 8.3%. So if it is 8.3%, now what happens? This is the fun part. If this is 8.3%, and let's assume we fix our alpha at 5%. Significance. Your p-value is greater than alpha, which means which means we accept null hypothesis now. Look at this, we accept null hypothesis here. Is something crazily wrong here? Look at this, in this what happens? We accept H0. So we accept H0 here, right? Because the p-value that we got is not less than 5%. If we choose p-value of 5%, if we choose a significance level of 5%, we are accepting it, which is actually incorrect. We should be rejecting it, right? We should be rejecting, not accepting it. So where does this fall now? Look at this. Where does this fall? Simple, one experiment, simple experiment. Where does this fall? The truth is, this is the truth. This is the actuality. This is the actual value. But what happened now? We accepted null hypothesis, which means what we have is a type 2 error in this situation. Okay, now you might say, come on, all that we learned till now gone down the drain. Now, there are two problems in this. One is our sample sizes are too small. Let's increase our sample sizes. Everything else, and again, there are a couple of very important things. These two distributions are not very far away. That's another thing. These two are fairly close. They're not very far away. At the same time, these sample sizes are quite small. Okay, let's do another example. Let's keep small sample sizes now. Keep the sample sizes the same. The number of resamplings also the same. Let's say we change the alphas. Alpha equals to 10 here. Let's assume alpha equals to 8. Then what happens? Okay, again, here also, if you think carefully, here also, xc is not equals to xt. Okay, we're just changing it. We're just playing around with it. Again, this is how you understand permutation testing through these simulations. Now let's just change it and quickly play around with this. Let's see what happens now. Okay. Again, very, very simple to play around. Okay, I'll just change. All we have to change is one line code. Okay, so the distributions are very close. So we observed two problems. One, the distributions are too close and the samples are too small. Okay, so let's play around. Okay, I'm just changing it to 8. Now let's see what happens. We're just changing the raw data itself. Okay, now what happens? What is the p-value that we got? Yes. Look at the p-value that we got now. The p-value that we got is 1.8%. What is the observed value now? Observed value is 0.03. Now this is, again, this is the PDF. I just discussed this earlier, right? This is the PDF of MIs. And the observed value is 0.3 something, right? Where is that? 0.308. Where is 0.308? 0.308 will be somewhere here. This is the observed. And there aren't enough values after that. So the distribution that the p-value that we got here is 1.8%. Okay, so let's go back to the drawing board. So we got 1.8%. So in this case, what error did we have? In this case, we had a type 2 error. In this case, perfect. This case is perfect. So as the distributions differ more, even though we have small sample sizes, permutation test is able to work well. Okay, let's do a slightly different experiment again. We are not done. So let's increase these sample sizes now. From 100, I'm changing it to 1000. From 100, I'm changing it to 1000. I'm just increasing it. I'm keeping the number of resamplings the same. Now here, I'm keeping the distributions also the same. What happens if the distributions are close? Again, remember, the distributions are close, but my sample numbers have been increased. Then what happens? Again, even in this case, your xc is not equals to xt. What happens now? By just increasing the number of samples, what happens now? Again, simple, quick, we can easily do that. Where are we? It takes again, this playing around of simulations is what gives you a lot of clarity in general. Okay, so let's just play around. Okay, takes a couple of seconds. What's happening now? Okay, we got these distributions, very close distributions. Oh, cool. Look at this. Our p-value is 0.4%. Very, very low p-value. Look at this. Our p-value is 0.4%. Okay, so the p-value that we got is 0.4%. Because the p-value is less, this is behaving as expected. So when the distributions are close, look at this, when the distributions are close, you need more samples. When the distributions are farther away, or more different, then even fewer samples is all right. That's a key insight that we cannot ignore. That's super duper important. Again, these simulations play a very important role in the depth of understanding. Okay, let's do one more thing. Okay, so what happens if m is small, n is small, right? So we have discussed this. What happens if I change k now? What happens if I change k? Let's play with k, right? Just because I can keep increasing k. So let's do another example. Imagine even if I have small samples, let me pick another color. Imagine if I have small samples, my k instead of 1000 is, let's say, 10,000, and my distributions are quite close. What happens now? Again, here also xc is not equals to xt. It's not equal. Now what happens? Let's figure it out, right? Fun, lot of fun. Again, this code is literally 10 lines, and I have actually appreciated and learned whole permutation testing through simulations like this. I think there is a similar assignment for some of our students in the diploma program, if I'm not wrong. So this is 10, 10, this is 10,000, and this we will change it to 9, right? So what happens now? Let's see. Okay, what happens now? No, it's not working out. Even if I keep changing m, look at this. Here I'm still getting, what is the value that we got here? We got 8.73% here. So the problem here is, even if I just keep increasing the resampling, look at this, I increase the resampling here. Even though I increase the resampling here, it's not working out because my data itself is so small, given that the distributions are so close. It's not working out. So this is again a type 2 error. This is a type 2 error. Right? And the problem here is that my sample sizes are too small. I think there is a small error here. Let me redo it, because I've not done this experiment before coming to the class. I thought I'll do it along with you. So let's just see this. I think there is a small code bug somewhere. A code bug as in I forgot to change something when we experimented. So let's go back and redo that, because 0.4% seems suspiciously low to me. Okay, so let's look at our setup. 1000, 1000, 1000, 10, 9. Okay, so 1000, 1000, 1000, 1000, 10 and 9. Okay, so because 0.4%, I think I did not change the Pareto distribution earlier from 9 to 8. I think somewhere I messed it up. See, I told you it cannot be done. Okay, so the p-value that we're getting here is 22.4%. What is the value that we have? 0.002. Okay, yeah. So this number is true for 8, not for 7, not for 9, right? So the key idea is this: as your distributions are getting closer, you need a lot more data. Even 1000 points is not sufficient. That's the key. Okay, so as your distributions get closer and closer, like for example this, right, your distributions are very close, so even having 1000 points, you will not get a p-value of your choice, or you will not get a sensible p-value, because you need far more data than this. Okay, so going back to, okay, it's already 12:53, so I'll quickly go through some quick ideas with you, and then we'll wrap up this session and start in the afternoon. So the idea here is this. These are some of the experiments that you can do given this code, right? So let me also share the code snippet. Let me share this in the chat window so that all of you can try this. Copy, so that all of you can play around with this code during the lunch break, right? I'm just pasting it here in the chat window. Okay, so the code, the questions that you should ask and simulate is this: what happens if m and n are small, like 100? And everything else stays the same. What happens as k increases to 1000? Initially, we did an experiment where k equals to 100. K equals to 100 is small. Typically, people use k, which is the number of resamplings, as 1000 or 10,000. Now, what if your m is very large and n is small? Then what happens? Again, you could also have this, right? That this is like different sized samples, not same sized. If this is 10,000 and this is 1,000, what happens then? Let's just see that, right? Let's just quickly see that. It shouldn't take us much time. So let's just quickly do some of these. Again, I want you to explore and play around with these. Change the distribution slightly, play around with. So if I change this to, Okay, let's say I leave it to this. One sample is 10,000. What is the number? One sample is 10,000, other sample is 1,000, and k equals to small. Okay, if k equals to, again, these distributions are very, very close. So let me just let me increase the gap between the distributions slightly. Okay, slightly. 10 and 8 instead of 10 and 9. 10 and 9 are very close, especially in the Pareto space. Okay, now what happens? Oh, your p-value is exactly 0, right? Your p-value is literally 0%. And the reason you're getting such a small number like 0% is because you have only 100 resamplings, right? So now what happens if again, I'm just playing around. What happens if I make the distributions close? What happens if the distributions are close? Again, n is large, which means our control is large, our treatment is small. Now what happens? And the distributions are very close. Okay, distributions are very close. What happens now? Your p-value is still close to 0. Again, this you should not trust. And the reason why I'm saying you should not trust this is because your resamplings are too few. Look at this. You're resampling, you're only resampling 100 times. You should ideally do at least 1,000 times. Okay, so play around with these values. So if I change this to 1,000, again, look at this. What do I have? I have 10,000 sized control. My treatment is 1,000 and my distributions are close, right? That's the case that we're looking at. Now what happens to p-value? P-value is still 0. It's actually doing very good. So what happens? So just a while ago, right? What happens if both of them are 1,000? Then what happens? I think then this will generate an error. I think, if I recall correctly. Okay, because if n is 1,000, m is 1,000, both same sized. Again, remember from 10,000 we came down to 1,000. So there is a significant difference here. And these two distributions are slightly different. Now, what is the p-value that we're getting? I think we're getting a p-value of 22.4%. See, the problem here is, look at this, the problem here is these two distributions are very close to each other and we only have 1,000 samples. If we have 10,000 samples even in one class, or if you have 10,000 samples in one class or in one group, then even though these distributions are slightly differing, it will catch that. That's the beauty of it. And cool. So what happens? What is the p-value? I think it will be low. Yeah, it's close to 0%. Close to 0%. Very, very good. So the idea here is you have to ask these questions. What happens if m is large, n is small, and k is small? What happens? Again, in medical domain, you often have situations where m and n are very small because oftentimes in vaccine design, right? You can't give a vaccine to 1,000 people or medicine to 1,000 people. You typically start with only 30 people. Your control will be just 30 people. Your treatment will also be 30 people. And you have to decide if there is a difference between the medians. For example, I'll give you a real concrete example quickly and wrap it up in medicine. Suppose you have control and treatment. Suppose this is given for hypertension, also called as high blood pressure, right? So there is some high blood pressure medicine that is created by a new company. So this guy says, hey, all the patients, okay, you're taking control and treatment. The control guys are taking some existing medicine. Okay, they're taking some existing medication. Okay, they're taking some existing medicine. The treatment guys are taking some new medicine. Okay, then now you say, hey, again, it's all randomly split. There are 30 people in the control and 30 people in the treatment. Now you say, hey, does the new medicine reduce the blood pressure? Again, let's assume these are hypertension or high blood pressure, right? These are people with high blood pressure. So does the distribution of blood pressures in the treatment, are they lower than in the control? Or on average, is the treatment blood pressures lower than the control blood pressures? When you say on average, you can use mean or median and things like that. But you might run into this world where this sample size is just 30. So that's a very important experiment that you should conduct. For example, imagine what happens if you make sample sizes 30 here. That's a lot of fun. So imagine if I make this as 30 and this also as 30. Number of resamplings, I can keep them whatever number I want. Doesn't matter. I can make them even 10,000 because I can't experiment on more than 30 people. I can't give this new drug to more than 30 people. That's the problem, right? So if I have 30, and imagine these two distributions are not very different, slight difference, then what happens? I don't think the p-value will be less than the significance, less than 5%. Yeah, it's about 12.61% here, not less than 5%. Now what happens again? Now what happens if if there is a significant difference. Imagine if this distribution, again, the treatment, let's assume, has a significant difference from control. They're significantly different. They're not the same. They're significantly different. Then what happens? Even though I have very small sample size, if I have to make a guess, I think it will work. It's 8.4%. Okay, not yet there. Not yet there. So probably the difference has to be more significant than just this, right? Probably this has to be something like some 7. Again, as I keep changing this alpha value, these two distributions are changing more and more, or they're differing more and more. Okay. So if these two distributions actually have significant difference, only then it will show, it will pass the p-value test. Okay, now it's about 5.8%. You still have to have significantly more difference than this. Again, this whole thing is all about playing with this experiment. Again, this whole code that we have, right? If I remove all of these links, right? Okay, let me just see if I have share access. Just a second, folks. I'm not sure if I've shared this with everyone. Just give me a second. Yeah, anybody can copy it. Okay, cool. Yeah, anybody can access it. So it's literally like what, 10, 20 lines of code. And you can do all of these experiments here very, very easily. Okay. So again, what if m equals to 30, n equals to 30, m equals to 20? What is the maximum value of k? Right. So, oh, this is a nice question. I completely forgot. But because since we don't have time, let me quickly answer this. Suppose if your control size is 30, your treatment size is 20, right? Then n plus m equals to 50, right? The question here is, what is the maximum value of k in this situation? What is k? K is the number of resamplings that you can do, right? So if you think about it, if the total number of people, the number of observations that you have is 50, how many, look at this, if n plus m is 50 and you have 50 places, right? Imagine that this is an array, index 1, index 2, index 3. How many ways you can order 50 elements in 50 positions? 50 factorial, right? I can place any of the 50 numbers here. Remaining 49 numbers I can place here. Remaining 48 numbers I can place here, and so on and so forth, right? So I have 50 factorial ways in which I can arrange these numbers. And for every arrangement, I can cut these numbers. I can say this is control and this is treatment, right? So if n and m sample sizes are small, then k cannot be very large. But in practice, even if k is something like 1,000 or 10,000, that's good enough for most real world situations. Okay, so don't worry about that. Even in small sample sizes, permutation testing can work well if the distributions are significantly different.